Good day, everyone, and welcome to episode 3 of the BET Masterclass series, Building Resilient Systems. My name is Ntabile Macheta, and I'll be your host for this session. At BET Software, our masterclass series is designed to share real world engineering insights, showcase our technical talent, and create meaningful conversations within the tech community. And today's session is no different. In today's session, the System Resilience series, we teach you how to design, monitor, and respond to system challenges in a way that keeps platforms stable and reliable, even under pressure. Leading today's masterclass is Stewart Burton. He's our subject matter expert on system resilience and incident response. Stewart brings extensive experience in designing resilient systems, monitoring infrastructure health, and responding to incidents in high impact environments. Today, he'll be sharing best practice approaches, industry patterns, and practical tools that you can apply to your own systems. Please note that this session is pre recorded, but we are live in the chat. So drop your questions as you watch, and our team will be sure to answer them. With that said, let's get started. I'll now hand you over to Stuart, who'll take us through today's session.
So, hi everybody, I'm Stuart. I'm a DevOps engineer at BET Software. My day job lives in that interesting pressure zone between developers shipping new features, infrastructure and DevOps teams keeping everything stable, and production incidents that always seem to arrive at the worst possible moment. So I spend a lot of my time thinking about and working on system resilience. So how do we design systems so that they can handle chaos? How do we detect issues early before customers shout? And when something does go wrong, how do we respond in a calm, structured way rather than panicking? So this session is part of the BET Masterclass series. It'll be aimed at DevOps, site reliability engineers, platform and infrastructure engineers, developers and technical leads, IT operations and support teams, as well as any non-technical leaders or even just interested individuals who want to understand the why uptime is such a big deal, as well as what goes into protecting said uptime. So as such, I'll keep the language reasonably accessible. If you're technical, there'll be enough details to relate to your day-to-day. If you're more on the product management side, you'll still be able to follow the story and you'll see where your teams need support. Okay, so let's switch to the roadmap slide, and then I'll run you through what we're going to cover over the next 40 minutes or so. So number one, why downtime really matters. So I'm going to be using the October 2025 AWS global outage as an example. 2, core principles for designing resilient systems. 3, monitoring, observability, knock, SOC, and alerting in practice. I'm going to include some tools like Prometheus, Grafana, Elastic, and Dynatrace. I'm also going to touch on AI enhanced observability in DevOps, AI ops, AWS DevOps agents, and how AI is changing incident response for the better and quite rapidly. We also got to touch on the incident response lifecycle from detection to recovery, which is going to be a little bit meaty. And then we're going to look at a natural realistic case study. So a month-end salary banking outage, which hopefully none of you experienced, but I'm sure all of you have. And then after that, we're going to look at post-incident learning culture, and I'm going to run you guys through an incident response playbook, which I'm hoping you should find invaluable. Okay, so by the end, you should have practical ideas you can take back to your own environment, regardless of whether you work in banking, betting, e-commerce, software as a service, or any sort of inline of business system. All right, so next slide, we're going to look at why uptime really matters. And we're going to start with the why, because it's important. So why is system resilience such a big deal? And why do we obsess over uptime and stress over alerts at 2 a.m.? So the global outage that AWS experienced in October 2025. So on the 20th of October, Amazon Web Services, who are the biggest cloud provider in the world, had one of the largest outages to date. So in simple terms, a combination of DNS and control plane issues in the US East 1 region went wrong. Services depending on that region started failing and returning errors. So because so many companies rely on AWS, the impact rippled out quite quickly. Within a short period, major consumers and customer apps slowed down or went down. Collaboration tools, some payment services, streaming platforms were also affected. So for many businesses, their applications simply stopped working, even though their own code hadn't actually changed on the day. So that incident made it very clear that even world-class platforms with thousands of engineers have failure modes. So When foundational infrastructure is disrupted, a huge number of downstream businesses feel it at the same time. So, and we all know users don't care whose fault it is. They just see their app is down and they get frustrated. So for companies that were running on AWS or similar providers, it was a stark reminder that relying on cloud doesn't remove the need for resilient thinking. If anything, it makes it even more important to understand dependencies and then also to plan for their failures. Okay, so we're going to switch to business impact in plain language. So we've all seen industry studies that estimate the cost of downtime for large organizations, thousands of dollars or thousands of rands per minute. But instead of exact numbers, I want you to think in terms of impact, right? So lost transactions, orders, payments, bookings, signups that have failed, operational disruptions. So things like staff time or manual workarounds, or chasing inconsistencies. The other side of that is the reputational damage that people have experienced. So social media complaints, negative reviews, loss of trust is a big one. And then there's also regulatory or contractual consequences that can occur. So software license breaches, penalties, and audits. So considering a few scenarios where downtime really hurts, a banking platform failing at month end when salaries are paid, or an e-commerce site failing over during a major sort of sale or marketing campaign, let's say like Black Friday, or ticketing service crashing when there's a concert or airline tickets opening. Or payroll system failing on payday, a SaaS production going down in the middle of business hours for its largest customers. Alrighty, I'm hoping I covered most of the example cases for you guys. So in each of these cases, a few minutes may be survivable, but an hour or two can become very expensive, and then a full day can cause long-term damage to customer trust. So when we at DevOps engineers or as platform engineers talk about uptime and resilience, we're not just talking about pretty graphs. We're talking about protecting revenue, protecting customer trust, and sometimes even people's ability to pay rent and their salaries on time. So it's pretty important. Okay, so why speed and communication matter? So incidents are inevitable. The key is how quickly that we handle those incidents, right? So the three things that I think matter most, we're going to look at early detection. So catching issues before customers and social media do, important. Number two, rapid mitigation. So taking smart actions that reduce impact quickly, even before the root cause is known. And then clear communication. So keeping internal teams as well as leadership and as well as customers informed with honest and timely updates is important. So in the AWS outage example and other recent incidents, the difference between chaos and a managed crisis was often how quickly teams noticed the problem and then how quickly they could roll back a bad change or reroute traffic, as well as how clearly they communicated that status. So that's the world that this talk is about, basically. So it's system design, observability, and then incident response, as well as the culture that turns ugly failures into controlled learning events. Okay, so let's switch to the next slide. It should be designing for system resilience. So resilience doesn't begin when the first alert fires. It begins with how we design and evolve our systems. I like to frame, resilience around 5 core principles. So number 1, eliminating single points of failure. 2, plan capacity for peak and not average. Number 3, design for graceful degradation. 4 is automate your recovery paths. And then 5 is practice failure, which I think is important. So game days and chaos testing. Alrighty, so if we switch now to eliminating single points of failure, if a single component can take down your entire platform, eventually, I guarantee you it will. So common single points of failure may include a single primary database with no replica or failover plan, a message queue running on one loading node, critical microservice deployed on a single instance, one DNS provider, one CDN, one edge location, one ISP, one data center region. I think you guys get the picture. So in most transactional platforms, some services are crown jewels, and those would be authentication and login, account and wallet services, any core transaction flows. Think of checkouts or payments, orders, trading, bookings, core pricing or inventory, and any rules engines. All right, so resilient design means that running multiple instances of critical services behind load balancers having database replicas or clustering plus failover procedures that have been tested. Redundant network paths and providers, and then also reducing blast radius so that one failed component only impacts a subset of users and not everybody. Okay, a good design habit is to ask yourself, if this component disappears at 3 p.m. on a busy day, what would it break? And how many users would feel it? So if the honest answer is everything, then that is a priority design problem. Okay, so moving on, we're going to switch to capacity planning for peak. Most ugly incidents come down to CPU pegging, memory exhaust, and connection pools maxed out, queue backups, or downstream dependencies being overwhelmed. In my experience, those are sort of the general go-tos. There are others, but those are the top ones in my opinion. The trap is designing for average traffic, right? But in real life, usage is spiky. So think month-end payday or tax deadlines, marketing campaigns, product launches or global events, or any sort of unexpected viral spikes. So resilient teams design for those peaks and not just for like a random Tuesday morning where everything is calm and complacent. So that means that, oh, excuse me, that means running realistic load tests that model expected peaks, and then also identifying bottlenecks, especially stateful components. So your primary databases, any shared caches or core services, as well as putting protections in place for caching, read replicas, ensuring rate limits, circuit breakers, back pressure, so that there is not one hotspot that doesn't collapse your entire system. So in practice, capacity planning is less about precision and more about avoiding being obviously under-provisioned at predictable peaks. So you'd rather be slightly over-provisioned and stable than save a bit and then deal with an outage later. Okay, so we're going to move on to graceful degradation. So, excuse me, we can't stop all failures, but we can choose on how they show up for us, right? So graceful degradation means core journeys should still work. So optional or heavy features can be temporarily sacrificed. Users can see a sort of slimmed down experience as opposed to a full crash. So some examples of this would be if they've added a recommendations or analytics widgets and those fail, then just hide them, but then still let users log in and complete transactions. If a third-party API is slow or down, make sure you use timeouts, circuit breakers, and fallbacks instead of letting that dependency hang or crash your entire flow. The other thing that DevOps engineers love is feature flags. So you can switch off heavy or experimental functionality without having to redeploy your code. And the goal of this in a particular failure, or sorry, a partial failure rather, users can still authenticate, they can still see core state, and they can still complete essential actions. So the nice to have elements that may disappear temporarily, but then obviously your critical flow remains available. Okay, that's going to move us along to automated recovery paths. And in a serious incident, people are obviously stressed and they are tired, and that is not the moment to rely on long wiki pages that no one's tested in a year, or that one engineer, the guru that remembers the sort of the magic commands. You all know you have one. So yeah, resilient systems have automated and well-tested recovery paths and automated rollbacks, CI/CD pipelines that let you revert to the last known good version with one action, and hopefully also includes basic smoke tests. Okay, automation failover scripts, orchestration for promoting replicas, failing over databases, or routing traffic to a healthy region. You should also look at auto-scaling policies that add capacity based on utilization and latency, as well as queue depth. And obviously, infrastructure as code or IOC and GitOps help a lot in this regard. So recovery steps should become code. It should be versioned, it should be reviewed, and it should be tested in lower environments, hopefully before you guys are testing this in prod. Okay, if your recovery plan lives only in someone's head, then that is not resilience, that is a hidden risk. Okay, so we're going to move along to practice, game days and chaos testing. Not a lot of people do this, but some people do. So resilience is like fitness. You can't just read about it. You actually have to train for it. So game days are basically planned drills where you can simulate specific failures. So for one example, let's pretend that our main database is down, and then you get everyone to walk through that failover. Or rehearse a response to key service returning HTTP 500 errors for 10 minutes. Chaos testing for the Netflix lovers amongst you is controlled experiments where you deliberately break things in a non-production environment at a high majority, and then you can move that carefully into production as well. So go ahead and sort of kill instances or introduce latency, black holing a dependency for a few minutes, etc. You guys get the point, right? The entire goal of that is to then uncover weaknesses in design, monitoring, or processes before they bite you in real incidents. Even simple chaos tests and staging can suffice. So missing alerts or poor failover behavior or even runbooks that are out of date can be problematic. Okay, alrighty. So switching to the next slide, we're now going to look at monitoring, observability, and security operations. If resilience was the hull of the ship, then observability is the radar and the instrumentation. Sorry for that analogy, but it's about the best one I could come up with. Okay, so the goal here is simple. Do not find out about incidents from social media or your call center. So find out from metrics, logs, and traces, and find out early. So the 3 pillars that we use is the metrics, which are time series numbers like latency, error rates, throughput, CPU, memory, and queue depth, which is great for dashboards and alerting. Number 2 is going to be logs, which is a detailed record of events. That'll be errors, warnings, business events, traces, and that is great for understanding what went wrong. All right. And then 3rd is going to be traces, which will be an end-to-end request for journeys across the services. And that is great for seeing where a transaction spent its time and then where it failed. Okay, cool. So we're going to switch to the next slide. And at BET Software, I'm going to show you what our stack includes. We use Prometheus for metrics. We use Grafana for dashboards and visualization. We also enable and use Elasticsearch for centralized logging. And then we leverage Dynatrace for application performance, service mapping, and anomaly detection. So other organizations may use Datadog, New Relic, Splunk, OpenTelemetry, or homegrown tools. If you guys want to put in the chat what you guys use, there are a plethora of different tools out there. The brand for me is less important than having good coverage across all 3 of those pillars. So Prometheus and Grafana for us is the metrics backbone. Prometheus scrapes numeric data. It'll do requests per second, error rates per endpoint, latency percentiles. It'll show us CPU and memory usage per node, things like that. So as an example, we'll define an alert rule, such as error rates greater than X% for Y minutes, or a 95% latency above a certain threshold, and then healthy instance counts below, say, a minimum, right? So Grafana will then sit on top of that as the visual layer, and then we'll have sort of high-level wallboard dashboards for overall health, service-specific dashboards for golden signals, business dashboards showing orders, logins, active users, and so on. And then during an incident, one of the first things we can do is open a relevant Grafana dashboard and ask what changed around the time that started. And then we can leverage Elastic or Elasticsearch or ELK for centralized logs and indices, right? So metrics often tell you that something is wrong. Logs usually tell you what and why that went wrong. App and infra logs are streamed into Elasticsearch, and then we can explore those with a tool called Kibana. So teams can search all services for a pattern, or they can filter logs by a correlation of, say, a user ID to pinpoint where errors have started and then the why, right? So during an incident, let's just say metric spike, we'll jump into Kibana, we'll filter by a time in a service, and then you can often see a specific exception that points to a code path or dependency. Dynatrace will be application performance monitoring and smart detection. On top of metrics and logs, Dynatrace gives us automatic service maps and dependency graphs, distributed traces that show end-to-end transactions. And this is also where AI-assisted anomaly detection and problem cards that can correlate symptoms and suggest likely root causes come into play, right? That has been very helpful, and the world is changing rapidly in that regard. So instead of 50 separate alerts, we might see one Dynatrace problem, which is beautiful, And it might say something like checkout error rate is increased, and then the likely root cause is latency on database X, and it's impacted services A, B, and C. That kind of correlation is invaluable where every minute counts, right? Because time is money in that regard. Okay, so we're going to switch to the next slide, eyes on glass. That's going to be the Networks Operations Center and Security Operations Center, which is 24/7 eyes on system. In many organizations, monitoring data is actively watched by a NOC, which, as I've just mentioned, Network Operations Center, they focus primarily on performance, uptime, and capacity. And then we get SOC, which is Security Operations Center, and then that focuses on threats, suspicious activity, and security incidents. Okay, so even without a formal NOC and SOC team or teams, I guarantee you someone at your company is playing these roles. So NOC monitors dashboards and alerts. They'll perform the first line triage and escalate to on-call engineers when patterns indicate trouble. SOC monitors security event tools. They'll investigate attacks and escalate security incidents into their own process for breaches and things like that. So from a resilience perspective, these teams provide early detection, a clear hands-off into DevOps or SREs, site reliability engineers, as well as engineering teams. They'll also provide continuous feedback into monitoring as well as protection strategies, which are also invaluable. Right, so now alert hygiene and avoiding alert fatigue. So a bad alerting can be dangerous, can be as dangerous as no alerting at all. So we aim for alerts that are always actionable, right? So if no one should act at a 2 a.m. alert, then we shouldn't wake that individual, that engineer up, right? And that alert needs to be prioritized as well. So prioritizations are mapped to severity levels. So we use P0, P1, P2, and P3. You guys may also know these as SEVs, and they are correlated. So they're grouped into meaningful incidents instead of sort of a flood of noise. Okay, so modern tools can help with a few things. So learning baselines, detecting anomalies, grouping related systems into a single problem, and then reducing duplicates. The whole goal is when someone's phone rings, they know that it really matters. All right, so we're going to switch to the next slide. So AI enhanced observability and DevOps. So as mentioned, over the last few years, AI has moved from a buzzword to real-world tooling in DevOps and operations. So AI Ops, or AI for operations, is about using machine learning to help detect anomalies, correlate events, suggest root causes, and remediate certain steps. So in practice, AI Ops tools can help cut down noise by grouping related alerts. They can detect issues humans may miss, and they can definitely speed up investigations by surfacing relevant graphs, blogs, and changes related to your symptom. So I'm not saying it's a magic bullet, but I am definitely saying that it is a powerful augment for any on-call engineers. So AI and DevOps agents, cloud providers, most of them have started embedding AI more deeply into their own tooling. So on the AWS side, we're seeing coding assistants that help generate and refactor application code. So security agents that review and design code for vulnerabilities, DevOps-focused agents that connect to observability data, configuration, as well as playbooks/runbooks. And then these DevOps agents aim to understand your architecture as well as your dependencies. They can go ahead and investigate incidents by pulling in metrics, logs, and traces. And then they can propose or even trigger runbooks to mitigate known failure modes. Okay, very valuable. Think of them as very fast, specialized junior engineers that are always up to date with context, but also still working under human supervision, hopefully. Okay, so AI enhanced developer experience, the other side of that coin. On the development side, it looks like, tools like Amazon Q Developer, GitHub Copilot, which I'm sure you've all heard of or used by now, and similar assistants are all good at suggesting code completions and refactors, generating unit tests as well as documentation. They're also used to explain error messages. They can do stack traces. They are also good at summarizing recent changes related to like a service. So for DevOps and platform work, this can look like quickly generating Terraform or a Kubernetes templates from intent level descriptions, or drafting a runbook or remediation scripts which engineers can then sort of refine, whether that be in Python or Bash or YAML or whatever it may be. We can also use them for summarizing deployment differences or diffs, and linking them to possible incidents as well as causes. So the pattern is consistent, right? Let AI handle the repetitive pattern-heavy tasks, and then let humans focus on design, decision-making, reviewing changes, and then also security checks and guardrails, and then clear ownership. So used well, AI can reduce toil and assist with both development and operations work. Okay, so we're going to switch to the next slide, and we're going to look at the incident response lifecycle. So this is quite meaty, so bear with me for a little bit. Even with great design and observability, incidents are still going to happen, right? So the question I'm going to pose to you is, how do we handle those, or how do we handle them? A simple incident lifecycle should look like this. We got it on the screen. So number 1, detect and declare. 2, triage and classify severity. 3, mobilize the team. 4 will be investigate and mitigate. After that comes communicate. There's recover and close. And then the last will be review and learn. So let's start with detect and declare. So incidents generally start from monitoring alerts or a customer reporting, monitoring alerts or customer reports. It could come from internal detection, someone notices an error in the logs or on a dashboard somewhere. Once we suspect that there is a real problem, then we quickly verify, right? So can we reproduce it? Is it impacting real users like now? Is it localized or is it widespread? So if it is clearly user impacting, then we have to declare an incident. Okay. Declaring an incident means we need to give it an ID as well as a start time. We then need to assign an initial severity level to that, create a dedicated communication space, a chat channel or a bridge call. We use Microsoft Teams. I think some of you may use Slack, but make sure that you treat it as a top priority until it is resolved, right? That'll take us to the next slide, which is going to be triage and severity. So we classify severity often using P0 to P3. In our space or BET software, people also refer to those as sevs or severities. So you can go Sev 1 to Sev 4 on a scale. And just to break this down for you quickly, P0 or Sev 1 is critical. So major functionality unavailable for a large subset of users, right? So serious financial, reputational, or safety implications. It is really, really bad. The P1 or Sev2, which is high, that's significant degradation, but also partial functionality exists. Hopefully workarounds may still exist. Okay. A medium, which will be a P2 or a Sev3, is noticeable issues, but with limited impact, right? And then a P3 or Sev4, which is low, that'll be minor or cosmetic and not super urgent. So having predefined criteria helps avoid debates in the middle of a crisis, and severity determines who must be involved, the update cadence, whether external communications or leadership escalation is needed, right? So mobilize the team for serious incidents. We immediately create a dedicated Teams channel, as mentioned, and start a live call. And then there are a few roles that need to be nominated for that call, right? So there is what's referred to as the IC, which is an incident commander, and they coordinate the response. They should set the priorities, and they should also track the decisions. Okay, technical leads need to be on that call for all affected services of the product. So app lead, database lead, infrastructure lead, etc. Whichever team is involved, their lead should be on that call. Communications lead needs to be there. If you guys have one, handles internal and external updates, as well as a scribe. So the scribe's job is to record key events, timestamps, as well as actions taken. Okay. The incident commander, just to note, also doesn't have to be the most senior engineer, but they must keep their responses structured. Okay. Investigate and mitigate. Investigation and mitigation should happen in parallel, right? So as mentioned previously, we use Grafana dashboards to see what changed. We'll use Dynatrace to trace slow or failing transactions. We have logs in Elk and Kibana, which we can use to find error patterns. Deployment history to check recent changes. And then using all of those, we should form an hypothesis. So for this particular example, say a new feature was deployed at 16:30 and is overloading service Y. So the mitigation is about reducing impact even before a full root cause is known. So let's run through some common actions quickly. Those common actions should include rolling back the deployments or disabling a feature via feature flags, scaling out app services or scaling up databases, failing over replicas or regions, and also temporary rate limits to non-essential endpoints, right? So after, excuse me, after each of those actions or after each action, you need to then watch the metrics. So are the error rates falling? Is the latency improving? Is resource utilization normalizing? If not, then revisit the hypothesis and then try the next option. Okay, communication as well. So throughout the incident, communication is a dedicated stream. So internally or internal, there should be regular updates on that incident channel. And there should be concise summaries. So what do we know? What are we doing? And what is next? Right? That's it. So for business and leadership, high-level summaries of impacted actions. So no speculation, clear facts versus the hypothesis that you were working with, right? And then customer-facing, status page updates, in-app banners, honest, brief, and acknowledging the issue and the status. Okay, I'm going to say that again. Honest, brief, and acknowledging the issues and the status. Okay. Good communication reduces noise. It builds and keeps trust. It also protects engineers from a constant interruption. Okay, and then that will take us on to recovery and closure. So once metrics and users experience, once metrics and users experience return to normal, we can then take a more deliberate approach, right? So verify core user journeys. Can users log in now? Can they see their balance? Can they complete critical transactions? And then once once that has been verified, maintain a watch period of say 30 to 60 minutes, just to make sure that there's no relapses or side effects. Okay. And then carefully reverse temporary actions that you guys did previously with the hypothesis. So scale back infrastructure. You can go and re-enable feature flags once you're confident in the stability and that it has returned. Okay. So the incident commander then declares the incident resolved, ensures a final summary and goes to the stakeholders, confirms notes and data for the post-incident review, and make sure that those have been captured. So now that the incident is officially closed, we'll move into learning. Okay, so if we switch to the next slide, it'll be the case study. I chose a month-end salary banking outage because I think most people should be able to relate to this, at least in South Africa, right? Okay, to make this concrete, let's walk through this incident of just a digital banking platform, no names mentioned. Okay, so even if you don't work in banking, the pattern's almost identical for any high-traffic transactional system. It just happens to be the scenario that I've chosen. Okay, so let's just say it's month end. It's a late Friday afternoon. Salaries have just landed in people's accounts. So users are busy logging into their banking app. They're checking their balances. People are paying rent and doing transfers. People are also using cards online as well as in the stores, or setting up and adjusting debit orders. Okay, so very busy. Everyone is busy on their app doing what they need to do. And then just say at 17:10 or 5:10 in the afternoon or evening, things start to go wrong. So support and social media light up. So you get messages like, I can't log into the app, or my card is being declined, or the app is just spins, or just spins on payments. So at the same time, while that is happening, you'll find monitoring fires up some critical alerts. So 95% latency for login payments, APIs taking more than 5 seconds, error rates start spiking on authentication and payment endpoints, database CPU hits 100%, and all the connections are maxed out on, say, like a core accounts database. Okay, cool. So this is quickly going to be classified as a P0 incident. Customers cannot reliably access or move their money on salary day. For detection and declare from the observability side, we could use Prometheus and Grafana to show those failed logins and payment spikes. Dynatrace is going to show traces where requests are stuck waiting on a core account summary service. And then Elastic and command logs will show something like timeouts waiting for the database connection. So SQL Server timeout starting at 17:05, around there. Okay, support is probably then going to call, support is probably going to confirm calls and chats from multiple regions, and it's not just one device or say one ISP. So because of all of the above, the on-call engineer is going to declare that P0 incident, and they're going to say a month-end banking outage with login and payments degraded, right? Nice and simple. So let's move on to the fix or the mitigation strategy. So, excuse me. So an incident chat is going to be created, as mentioned. We're going to need the application, database, and infrastructure, as well as DevOps reps pulled into that call. Roles will be assigned, and then mobilization and the initial hypothesis is going to kick off, right? So in the war rooms or the Teams call, a DevOps engineer will likely be sharing the banking API's golden signals on a dashboard. The IC or incident commander is going to summarize login and payments are slow or failing for many users. Core accounts, database, CPU sitting at 100%, and that started at around 17:05, which aligns with the peak of month-end traffic. Okay, the teams are probably going to split their focus then. The apps team is going to go and check their deployments and see that a new Smart Insights feature went live at lunchtime. So the database team sees that heavy aggregation query against hot tables is now being executed on every login. And the infrastructure team is going to confirm that app services are healthy, but the threads are largely blocked, waiting on said DB responses, right? So traffic is high, but it's consistent with month-end patterns. So with all of that, the working hypothesis will be something like the Smart Insights feature has triggered an expensive aggregation query on every login. So under peak load, that is now overloading the accounts database. And other operations like login and payments are being starved, causing the timeouts and the failures. So the mitigation then is to protect the core journeys, as we mentioned earlier. So the incident commander then coordinates. So he's going to, one, feature flag rollback, disable the Smart Insights widgets, right? So users can still log in, but without that heavy query running. Two, database capacity. So temporarily scale up the database, which would, and then also stop any long running queries or non-critical jobs that will be competing or contending for resources. Okay, the other thing that they can do is some traffic shaping. So verify the API tier scale, add temporary rate limits on non-essential APIs so that the core pathways get prioritized. Okay, and then within 5 to 10 minutes, hopefully they see that the DB CPU drops from 100% down to 60 or 70%. That 95% latency on logins, payments, APIs are now falling to under 800 milliseconds and no longer above 5 seconds. And error rates are decreasing towards their baseline. So users can now log in, they can see their balances, and they can make payments and transfers. So some users may have experienced earlier failures or delays, but now the prolonged outage has been avoided. The communications lead should then post. We are experiencing degraded performance due to high month-end traffic, combined with the new insights feature. Services are now recovering and processing normally, and obviously we apologize for the inconvenience. Okay. Also, nice and concise. So follow-up improvements. Once everything is stable and that incident has been closed, the team is going to go ahead and capture some lessons. So the Smart Insights feature that was deployed needs to be redesigned so that heavy analytic queries run against, say, a read-optimized store, or results are sort of pre-aggregated or cached, and login path then the login paths retrieve sort of lightweight data. Okay. The other thing is load tests need to be updated to include realistic month-end patterns, and then combined usage of logins, payments, and insights. Okay. The other thing they can do is add a new Grafana panel to track sort of health and latency of that insights feature. Highlight database saturation during sort of known peaks would also be useful. Okay. From a DevOps perspective, a runbook can be created or updated if they have one for the core banking DB saturation during peak, and then that should document symptoms, likely causes, as well as mitigation steps. Okay, so then in the post-incident review, those processes, excuse me. So in the post-incident review, processes issued are also discussed, right? So how did this feature reach production without realistic peak load tests? Valid question. Do we need stricter changes for reviews or core data paths? Do we need better do we need better per feature observability to spot impacts before they spill into core journeys? A lot of questions like that would be very, very helpful. Okay, so thanks for bearing with me for that case study, but I did all that just to illustrate that a well-intentioned feature can create serious incidents if performance isn't fully understood under peak load. So feature flags, observability, and structured response can limit impact. And then also that a learning culture turns incidents into lasting improvements. I think that is very important. All right, so post-incident learning and culture, very valuable. Fixing the immediate problem is only half of the work. The other half should be that you guys learn from it, right? Or learn from those scenarios. So I'm a big proponent for blameless post-incident review. So for significant incidents, a P0 or a P1, you should run that review within a couple of days. And then the participants for that should include the incident commander, key engineers, representatives from operations, products, cloud, infrastructure, DevOps, sometimes even business, depending on what the incident may have been, right? The review should cover a timeline. So when did it start? When was it detected? And what actions and what order did those occur? Okay. Impact. So what user journeys were affected, for how long, and any means or measurable business impact. Okay. Root cause and contributors. So technical will be design flaws, missing indexes, misconfigurations, or say dependency failures. Process, that'll be gaps in testing or unclear ownership or any documentation issues. And then also what went well. So did we detect it early? If there was a detection, great. Were there clear roles? And then also useful runbooks or playbooks are important. Okay. Then move on to what can be improved. So delays in detection, were there any? Did we miss any dashboards? Were the tools slow or were there any slow processes that we need to work on? All right, all of that will then lead us to action items. Okay, so concrete tasks, and those will have owners and dates to make people accountable for their action items. All right, so the tone of this should be blameless. The entire goal of this process is to understand how the system, the code, infrastructure, the processes, and the culture allow this incident to occur or to be worse than it was needed, right? All right, cool. So we're going to switch to the next slide, and that'll be tracking improvements. So those are going to be metrics. So MTTD and MTTR and trends. So over time, you should track mean time to detect as well as mean time to recover. So MTDD, how quickly you notice the issues, and then MTTR, how long from detect to like a normal service. Okay. Incident frequency and patterns. So how many P0, P1s per quarter, or are repeated incidents in the same components. So what we want to see is MTDD decreasing, which will be earlier detection, and then MTTR also decreasing, which will be faster mitigation, right? So repeated incidents should be declining. It means we're fixing root causes and not just symptoms. These metrics also justify investments in observability, automation, capacity, as well as technical debt reduction. Okay, so let's switch to the next slide. I'm going to discuss reliability as a feature. So we treat reliability as a product feature and not a background concern. So that means that we need to define some SLOs, and SLOs are service level objectives for key journeys, right? So an example of this would be, say, 99.9% of logins need to complete within 1 second, or 99.95% of payments complete without error over a 30-day rolling window, things like that. So From these SLOs, we can then derive error budgets, and that's how much unreliability we can tolerate in a certain period, right? So if we burn through error budgets, say we're slow or pause a new feature. Sorry, if we burn through error budgets, we should then slow down or pause new feature work and then refocus on stability. So hardening or refactoring and debt reduction, right? So this should create a shared understanding between engineers and business. So when reliability is on track, we can push features harder. But when reliability slips, we need to then go back and prioritize or reprioritize stability to maintain customer trust. Okay, cool. So that is going to take us to the next slide, which is the incident playbook. So all of this is going to come together in a living document. That living document is the incident response playbook. If you guys haven't already, you should be able to find that with a QR code or in the description in the chat. Feel free to download it. And that's going to run you through a few things. Okay. So a playbook will typically include roles and responsibilities. So everything I spoke about earlier, the definitions of IC, technical leads, communications, and the scribe. That book's also going to have escalation paths and on-call rotations. It'll have the severity models, so the P0 to P3 with examples tailored to your domain or your company, as well as a standard workflow, right? So that'll be a step-by-step guidance for detection, declaration, triage, mobilization, mitigation, communication recovery, and review. All right. It'll also include a checklist for each phase. And the point of that is to reduce cognitive load under stress. Okay, because during an incident, everybody is stressed. It's nice to have a handbook and a checklist to step-by-step run through. Okay. It's also going to contain runbooks or playbooks, which are scenario-specified procedures, right? So, for example, high DB latency with connections exhausted, or authentication degradation, cache cluster failure, third-party API outages, anything that is relevant to what you guys experience and what your company has to deal with, right? So each runbook, each of those should include symptoms, common causes, diagnostic steps, as well as mitigation options. Okay. It should also have tooling pointers. So links to dashboards, log views, tracing tools, and even ticket templates if you guys want. Status page endpoints, as well as communication channels. So you can find everything that you need. Okay. That playbook, it's important, also needs to be version controlled, and then it needs to be updated after real incidents. So you should use it in game days so it becomes familiar and trusted, but please make sure that you guys keep it updated and tweak it as incidents grow. It becomes more and more valuable the more you do that. All right, cool. So switching to the next slide, closing. I'm just going to tell you guys what we looked at in summary. So we looked at why downtime matters. So from large outages to everyday disruptions. We had a core design principles for resilience chat about single points of failure. We went through peak for planning, graceful degradation, automation, and practice. We looked at observability in practice, which is the metrics, logs, and traces, and knock and sock. We looked at some of the tools that we use, so Prometheus, Grafana, Elastic or Elk, as well as Dynatrace, and any of those tools you guys may use that may differ. We touched on AI and AI ops and how that helps us to detect and correlate and respond faster. And then the incident respond lifecycle, which was, again, detect, declare, triage, mobilize, investigate, mitigate, communicate, and recover. Alrighty. And then we also looked at a case study on how a structured response can limit impact. Okay, cool. So hopefully come payday, we are all good. We also touched on post-incident learning, SLOs, error budgets, and also the value of having sort of that living playbook. Okay, so if there's one idea to take away from this, incidents are inevitable and chaos is optional, right? So incidents is not an accident. Sorry, resilience is not an accident. It's something that we design for, we should practice, and we should continually improve. Okay, so whether you're a DevOps engineer or a platform specialist, a developer in general, or a product lead, you have a role in this to play, right? So push for better observability, invest in automation, participate in post-incident reviews, and then treat reliability as a first-class citizen, please. Alrighty, cool. So thank you for spending time with me as part of this BET Masterclass series. If you guys have any questions, I will feed back to you at the bang. Thanks. Bye.
Thanks for such an amazing and insightful session, Stuart. Like Stuart said, relying on the cloud does not remove the need for resilient thinking. Thank you for joining us for episode 3 of the BET Masterclass series. We hope that this session has given you practical insights into building resilient systems, responding effectively to incidents, and reducing downtime in real world environments. Don't forget to check out the link in the comments to access your system resilience playbook, which you can use as a reference long after the session is over. Be sure to follow BET Software on LinkedIn, YouTube for future masterclasses, resources, and upcoming episodes in the masterclass series. Thanks again for joining us, and we look forward to seeing you in the next episode.